So, welcome to Engineering Mathematics 2 session. Friends, my name is Dr. Shivlingappa Sangappa Benchali, working as a professor at Department of Mathematics, Basaveshwar Engineering College, Bagalkot. Friends, here I am going to discuss about differential equation 2. The contents of differential equation 2 are linear differential equations with variable coefficients, solution of Cauchy's and Legendre linear equations. So, along with these things, I am going to discuss about what are the non-linear differential equations. It means I am going to discuss about equations solvable for P, equations solvable for Y, equations solvable for X, general and singular solutions, Clairaut's equations and equations to reducible to Clairaut's form. For all these contents, I am going to refer the following textbooks. So, one is Higher Engineering Mathematics by B.S. Grewal and Advanced Engineering Mathematics Gill and Gullin, and Engineering Mathematics by Garg and Gupta, and one more important textbook is Differential Equations by George Simmons, right. So, you can refer these textbooks for the above contents. Not only these textbooks, if you feel that some other textbooks are good for the above contents, you can refer those textbooks also. Okay. So, now I have planned to cover the above contents in this forum. So, first I am going to discuss about a linear and non-linear differential equation. So, for example, you may ask, how do we recognize a linear differential equation and how do we identify a non-linear differential equations, right. So, it means a linear differential equations with variable coefficients. I hope in the last 2-3 sessions you are already familiar with a linear differential equation with variable constant coefficients, right. Now, I am going to introduce linear differential equations with variable coefficients. Is it clear, right. So, along with that we want to discuss about Euler-Cauchy linear equation, Legendre linear equation, and after completing these types of differential equations, I am going to discuss about non-linear differential equations of the first order and higher degree differential equations. It means we want to discuss or we want to solve some examples about equations solvable for phi, equations solvable for y, equations solvable for x, Clairaut's equation, right. So, I have planned like this. Okay. So, now you may ask, what is the purpose of this session, right. The purpose of this session is I am going to define some objectives of the session, right, and what are the learning outcomes. Here I am going to introduce some types of differential equations, right. So, after this session you are going to learn, right. It means after this session you may be able to write what I have learned from this session. Is it clear, right. And here I am going to discuss about first order differential equation. You are already familiar with first order differential equations and you are already familiar with second order differential equations also. Is it clear, right. And various methods to solve differential equations with variable coefficients, right. So, point 3 is already familiar with us. You have studied first order as well as second order differential equations, and in this session I am going to introduce some methods to solve differential equations with variable coefficients. Then we shall discuss about understand the process of solving Cauchy linear equation, how we are going to solve a Cauchy linear equation, solutions to second order homogeneous Cauchy linear equation, then solutions to second order non-homogeneous Cauchy-Euler equation. It means I will consider a differential equation, a right hand side may be equal to 0, may not be equal to 0, right. The given equation may be an second order differential equation. If the right hand side is equal to 0, then I will call it as it is a homogeneous equation or homogeneous Cauchy-Euler equation. So, in such a situation, how we are going to find out the solution of such type of differential equations? Suppose if the right hand side is not equal to 0 and all the coefficients are variables, such type of equations you may call it as an non-homogeneous Cauchy-Euler equation. Suppose if the given equation is an non-homogeneous Cauchy-Euler equation, how we are going to find out the solution, right? So, we shall discuss all these things in this session. Okay. First, I want to define the objectives of the session. To enable students to apply the knowledge of mathematics in various engineering fields by making them to learn the following. Suppose if you want to solve any engineering problem, then we need the following things. So, first one is you must be able to solve Euler-Cauchy linear differential equation, and second one is Legendre linear equation, equations solvable for p, equations solvable for y, equations solvable for x, and Clairaut's equation, right. So, if you know, then you must be able to attempt to solve any engineering problem. Okay. Then you may ask, what are the learning outcomes? So, upon successful completion of a linear differential equation with variable coefficients, it is expected that a student will be able to do the following. So, be familiar with terminology such as variable coefficients, linear operator, auxiliary polynomials, particular and complementary solutions. Friends, so far you have studied a differential equation. I hope you must be able to identify the given differential equation, right. Exactly in the similar way, you must be able to find out order and degree of a differential equation. Is it clear? Exactly in the similar way, you must be able to identify variable coefficients and what are the linear operators. Say for example, if I write d by dx is an operator, or sometimes instead of d by dx we will use capital D as an operator, and we must be able to write down an auxiliary equation. Here you must be able to know the word auxiliary polynomials, is it clear, and particular and complementary solutions. As I have mentioned, sometimes the given equation may be an homogeneous equation or the given equation is an non-homogeneous equation. How do we say that given equation is a non-homogeneous? If the right hand side of the equation is not equal to 0, then we call it as an non-homogeneous equation. So, if the given equation is an non-homogeneous equation, then the solution of such a type of differential equation is y is equal to, you want to write down the complementary function plus particular integral. Is it clear? Right. So, if the right hand side is equal to 0, then you want to write down y is equal to complementary function becomes the solution of the given differential equation. Is it clear? Right. So, particular solution means, so we know that a general solution may contain some arbitrary constants, then you can replace some arbitrary constants by a particular number. Say for example, our solution may contain C1 and C2 as the arbitrary constant. Now, I want to replace C1 by 1, C2 by 2, then that becomes the particular solution. Is it clear? So, like that we will come to know particular and complementary solutions. Find the general solution of a second order differential equation or higher order linear homogeneous equations with variable coefficients. Is it clear? So, similarly, we are going to find out the general solution of second order linear non-homogeneous equations with variable coefficients, or it may be an higher order linear non-homogeneous equations with variable coefficients. It means after the completion of this session, you must be able to do all these things. Okay. Suppose if I want to solve a linear differential equation with variable coefficients, it may be an second order differential equation or it may be an higher order differential equation. So, I must know the preliminary things or we must know the preliminary things, right. Then you may ask, what are the preliminary things? One should know if he or she want to solve an linear differential equation with variable coefficients. So, for example, you must be able to identify an ordinary differential equation, or I can say that ordinary and partial differential equation. Ordinary differential equation means any equation containing ordinary derivative. Ordinary derivative means, say for example, given equation may contain dy by dx or capital D into y. Is it clear? Such type of equations we call it as an ordinary differential equation. In the given equation, highest derivative is, say for example, dy by dx is present, then we can say that it is a first order differential equation. Is it clear? So, similarly, we call it as an partial differential equation, an equation containing partial derivatives. Partial derivatives means, I hope you know the symbol dou by x upon dou by y, etc. A differential equation may contain partial derivatives, then we call it as an partial differential equation. Here I am not going to discuss about partial differential equation. Is it clear? Order and degree of a differential equation. As I have mentioned, highest derivative is d square y upon dx square is present, then you can say that it is a second order differential equation. Suppose our differential equation containing d cube y upon dx cube, then you can say that order is 3, and in the given differential equation highest derivative is nth derivative d raised to n y upon dx raised to n, then you can say that it is nth order differential equation. Is it clear? How do you identify the degree of a differential equation? First you want to identify highest derivative, then its degree is the degree of the differential equation. Say for example, in an given equation d square y upon dx square is the highest derivative and its degree is 2, then it becomes a second order second degree differential equation. Is it clear? Suppose d cube y upon dx cube is the highest derivative present in a given differential equation, its degree is 1, then we call it as an third order first degree differential equation. I hope you have studied all these things in the last 3-4 or in the previous sessions. Is it clear? And sometimes you must be able to convert the given equation into an ordinary differential equation, right. So, it means the given equation is not an differential equation. Is not an differential equation means given equation does not containing dy by dx. In such a situation, we will say that the given equation is not an differential equation, but we can make it as a differential equation. Is it clear? How do you make it as a differential equation? I will give one simple example. Y is equal to mx, right. I will ask, is it a differential equation? You will say that clearly it is not an differential equation. How do you say that it is not an differential equation? Because y is equal to mx does not containing dy by dx. That is why it is not an differential equation, but it can be made it as a differential equation. How do you make it as a differential equation? It is very simple. They have given y is equal to mx. Now, I want to differentiate with respect to x. So, dy by dx is equal to m is a constant. I will keep m as it is. Then derivative of x with respect to x is 1, right. So, it means I will write down dy by dx is equal to m, and from the given equation y is equal to mx, I will find out the value of m y by x. So, it means dy by dx is equal to y by x is the differential equation. It means this is one method to form an ordinary differential equation. So, like that you must be able to convert a given equation into an ordinary differential equation. Is it clear? Right? Here we have converted by eliminating an arbitrary constant, say m. Right? Okay. Differential equations of the first order and first degree. So, you are already familiar with all these methods. Suppose equations whose variables are separable. It means they have given a differential equation and I am able to write down all the variables one side. Variables one side means functions of x and dx one side, functions of y and dy another side. Then you may call it as an variables are separable. Is it clear? Then you can integrate immediately. If the given equation is an homogeneous equation, you know the method. How do we find out the solution of homogeneous equation or variable separable equation or equations are reducible to homogeneous equations. Suppose if the given equation is not an homogeneous, then it can be converted into a homogeneous equation, right? Or the given equation is an linear differential equation. So, you are already familiar with the first order linear differential equation. The general form of the first order linear differential equation is what? I hope you will remember the linear differential equation means first order linear differential equation can be write down in the form of dy by dx plus py is equal to q, right. So, where p and q are functions of x. So, such type of equations we call it as a linear differential equation or first order linear differential equation, or sometimes you can say that linear in y. Is it clear? I want to repeat once again, dy by dx plus py is equal to q. So, that equation you may call it as it is linear in y. Sometimes the given equation may not be in the standard form. May not be in the standard form means the given equation is not in the linear differential equation form, but we can reduce it into a linear differential equation. Such type of equations we may call it as an Bernoulli equation. Is it clear? So, initially when we observe the Bernoulli equation, it may not be in the linear differential equation form. It means dy by dx plus py is equal to q form, but we can make it as an dy by dx plus py is equal to q. That is why we call it as an Bernoulli equation, or sometimes we call it as an reducible to linear form. Okay. So, we have already discussed all these types of differential equation. It means you are already familiar with these equations. Now, I do not want to solve any example about these forms. Is it clear? So, along with those equations, we have also studied exact differential equation. Is it clear? So, I hope still you remember m into dx plus n into dy is equal to 0. So, it is called an exact differential equation. You want to verify the condition. If the condition is satisfied, then we call it as an exact differential equation. Then we will find out the solution of the exact differential equation. And if the given equation is not an exact form, it can be reduced to exact form. So, this type also discussed in the earlier sessions. Suppose if the given equation is an second and higher order differential equation, how we are going to find out the solution? Is it clear? Second and higher order differential equation with constant coefficients. So, I think you have studied this type of differential equations in the earlier sessions. I am not going to solve any this type of examples. Now, I want to discuss about second and higher order differential equation with variable coefficients. Is it clear? So, in this case also you have studied it may be an homogeneous equation, it may be an non-homogeneous equation, right. So, if it is an homogeneous equation, means they will give a second order differential equation and right hand side may be equal to 0. Then you want to write down the auxiliary equation, then you will get 2 roots. If the order is 2, then depending upon the 2 roots you want to write down the solution. So, for example, sometimes you may obtain 2 different roots, for example, 1 and 2, right. Sometimes you may obtain a real and same roots, for example, 2 and 2. Sometimes you may get complex roots 1 plus I. Is it clear? Right. So, in all those cases you will get different type of solutions. you are able to express y is equal to c1 into e to the power 1 into x, c2 into e to the power 2 into x, if the roots of the given equations are 1 and 2. Is it clear? Suppose if the roots are 2 repeated roots, how we are going to write down the solution in case of a second order differential equation with constant coefficients? It is very simple. Y is equal to c1x plus c2 into e to the power 2x. Is it clear? Or sometimes you are able to write down y is equal to c1 plus c2x into e to the power 2x. Is it clear? Like that, if the roots are complex, 1 plus I, or in general alpha plus or minus I into beta. In that case, how we are going to write down the solution of second order differential equation with constant coefficients? It is very simple. Y is equal to e to the power alpha into x into the bracket c1 into cos beta x plus c2 into sin beta x. Is it clear? So, you know all these things. Now, I want to extend the same concept to solve a differential equation with a variable coefficients, right. So, it may be an second order differential equation. What are the methods to solve such type of differential equation? Such type of differential equation means differential equations with variable coefficients. Say for example, the given equation or general form of such type of equation may be in this form: y double prime plus f of x y single prime plus g of x into y is equal to 0. Here it may be a polynomial, means f of x may be a polynomial and g of x may be a polynomial, or it may be a simple function of x. F of x and g of x may be a function of x. Is it clear? Okay, right hand side is a 0. So, you assume that they have given this type of equation. You may ask, how do we solve this type of equation? So far, we have not solved this type of equation, but we have solved a linear differential equation with constant coefficients. Constant coefficients means, say for example, the coefficient of y double prime is 1, the coefficient of y single prime is 2, right. The coefficient of y may be 3 is equal to 0. So, you have solved such a type of differential equation, but I think you have not solved this type of equation. Here the coefficient of y single prime is a function of x and the coefficient of y is a function of x, right. Then you may ask, okay, this is the given equation, can you tell me how do we find out the solution of this type of equations? Okay, before obtaining the solution of this type of equation, first I will give how many methods are there to solve this type of equations. Am I right? Okay. So, method number 1. So, first method may be like this: missing y term. It means given equation is like this, instead of giving like this, and given equation may be in this form. Sometimes they may give an equation like this: y double prime plus function of x into y single prime is equal to 0. So, it means you observe this term is missing, right, last term is missing. So, if the given equation is in this form, we call it as a missing y term and we can find out the solution of this equation. So, this is one method to obtain the solution of a linear differential equation with variable coefficients. And another method is Cauchy-Euler equation. Say for example, given equation may be in this form: x square y double prime plus a into x into y single prime plus b into y is equal to 0. Here you observe the coefficient of y double prime is x square, right, and the coefficient of y single prime is a. A is what? A is some constant and x is a variable, right. Similarly, b is a constant into y is equal to 0. If the given equation is in this form, then it can be write down in this form: y double prime plus a by or a divided by x into y single prime plus b divided by x square into y is equal to 0. You may ask, how do we get this equation? Throughout divided by x square I hope you can obtain this equation, x square into y double prime divided by x square. X square cancels with x square, a into x divided by x square, x numerator containing x, denominator containing x square, x cancels with x. What is the remaining thing? A remaining thing is a by x. Last term is plus b into y divided by x square, or it can be written as b by x square into y is equal to 0. Then we can obtain the solution of this equation. We call it as this is another method. And third method is we call it as reduction of order. Reduction of order means, say for example, the given equation may be like this. So, can you tell me what is the order of this differential equation? So, clearly we can say that the order of this differential equation is 2. How do we say that it is 2? Because highest derivative is 2. It is containing y double prime. So, that is why we can say that so it is a second order differential equation, and we know that if it is a second order differential equation, you will get how many roots from the auxiliary equation? You will get 2 roots. It means you can say that you may obtain 2 solutions. Is it clear? Right? Out of 2 solutions, sometimes one solution may be known. We want to find out another solution. How do we find out the another solution is the question, right? So, in such a situation, we can use the third method, and we may call it as a reduction of order. Is it clear? We call it as a reduction of order. So, by using this method, we can find out one more unknown solution. Is it clear? And give, for example, a given solution may be written in this form: y1x is equal to e to the power minus 3x is a solution of the given equation. Is it clear? So, here they are given y double prime plus 6 into y single prime plus 9 into y is equal to 0, and they have given a one solution. Now, I want to find out the second solution. So, there is a particular formula or particular method, we call it as an reduction of order method. By using that method, we can find out y2 of x. Is it clear? And one more method is there, we call it as an Legendre linear equation. Suppose if the given equation is in this form, 5 plus 2x whole square into y double prime minus 6 times of 5 plus 2x into y single prime plus 8y is equal to 0. Okay. So, this is our differential equation. Now, I want to find out the solution, right. How do we find out the solution? By using the method of substitution. Is it clear? So, what you want to substitute? Put 5 plus 2x is equal to e to the power z. I am going to replace 5 plus 2x by e to the power z. This implies I can write down z is equal to log of 5 plus 2x. So, by using this method, I can find out the solution of this differential equation, and this method we call it as an Legendre linear equation method. Okay. So, this is the fourth method. And what is the next method? We call it as an method number 5, power series method. Suppose if the given equation is y double prime plus a is a function of x divided by x into y single prime plus b is also a function of x divided by x square into y is equal to 0. So, given equation is in this form. You observe in all these equations, right hand side is 0. Okay. Now, we want to find out the solution, and you can assume the solution of this type of equation may be in this form. Y is equal to, I can assume C naught plus C1 into x plus C2 into x square plus C3 into x to the power 3 plus so on plus Cn x raised to n plus so on. Is it clear? So, by assuming this form, I can find out the solution of this differential equation. Okay. And one more method is method number 6, and you may call it as an Legendre equation. The given equation may be in this form: 1 minus x square into y double prime minus times of 2 into x y single prime plus n into n plus 1 into y is equal to 0. This is the given differential equation. Now, I want to find out the solution of this differential equation. In this case, I want to assume the solution of this differential equation is in this form: y is equal to a naught plus a 1 x plus a 2 x square plus a 3 into x to the power 3. Next term may be like this: a suffix 4 x raised to 4. Its next term may be a suffix 5 x raised to 5 and so on. In general, a suffix n x raised to n plus so on. Its next term, if you want to, or if you are willing to write, you can write down a suffix n plus 1 into x to the power n plus 1 and so on. Is it clear? So, by assuming this, you are able to find out the solution of this differential equation, and this method is also called Legendre differential equation. Is it clear? So, by assuming this means you want to find out the value of a2, the value of a3 and the value of a4 and so on. You want to find out all those values in terms of a naught and a1. Then you want to substitute in this equation, that you may call it as a solution of the given differential equation. I hope in the higher semester you are going to study this method. Along with these methods, and we can solve a linear differential equation with variable coefficients by using one more an important method. What is that method? Bessel's method. We call it as an method number 7, or simply we call it as an Bessel's differential equation. So, this differential equation is called Bessel's differential equation. You observe the coefficients, all the coefficients are variables, right. It means the given equation is in this form: x square into y double prime plus x into y single prime plus x square minus n square into y is equal to 0. Then you can assume the solution of this differential equation is in this form. In this form means you can assume y is equal to x to the power m into the bracket a naught plus a 1 into x plus a 2 into x square plus a 3 into x to the power 3 plus next term is a 4 x raised to 4 and so on, a n x raised to n plus so on. Is it clear? So, by assuming in this form, we can find out the solution of this differential equation. It is also like a Legendre differential equation. Here also we want to find out the value of a2, the value of a3, value of a4 and so on, the value of a n. Then you want to substitute all those values in terms of the assumed solution. I hope your final solution may be in terms of a naught and a1. That becomes the solution of the Bessel's differential equation. Okay. So, we have discussed various methods to solve a linear differential equation with variable coefficients. Here I am not going to discuss all those methods, right. So, if you are interested, you can go through all those methods, because according to our curriculum, I want to discuss one method is enough to solve a linear differential equation with variable coefficients, right. So, before solving a linear differential equation with variable coefficients, I wanted to give how you are going to recognize a linear differential equation, right. And in the next session, we shall discuss about a non-linear differential equation, right. And we can define a linear differential equation as follows: a differential equation in which the dependent variable and its derivative appear in the first degree only and are not multiplied together is called a linear differential equation, otherwise a non-linear differential equation. Is it clear? We can define a linear differential equation in this form. Then you may ask, right. What it means? Here I have written with red color dependent variable. What is the dependent variable in dy by dx? Is it clear? Because every differential equation containing dy by dx, then you must be able to identify what is the dependent variable, what is the independent variable. So, for example, this equation containing dy by dx, can you tell me what is the dependent variable, what is the independent variable? All of us know that y is the dependent variable and x is the independent variable, right. So, definition suggests us or says that dependent variable and its derivative, it means y and dy by dx, right, appear in the first degree only. Here the degree of dy by dx is 1 and the degree of y should also be 1, is it clear, and are not multiplied together. I cannot write y into dy by dx, is it clear. In such a situation, we call it as a linear differential equation. It means in the given differential equation, you have to verify whether y into dy by dx is present or not, is it clear, right. If it is not present, then you can say that it is a linear differential equation. Suppose if you find y into dy by dx, then you cannot say that it is a linear differential equation, is it clear. Okay. I hope now you are able to identify a linear differential equation. I am able to write down the general form of an ordinary linear differential equation of nth order. How we are going to write down? In this form we are able to write down d raised to n y upon dx raised to n plus p1 into d raised to n minus 1 y divided by dx raised to n minus 1 plus p2 into d raised to n minus 2 y divided by dx raised to n minus 2 plus p3 into d to the power n minus 3 y divided by dx raised to n minus 3 plus so on. Is it clear? Suppose if you want to write its next term, what is the next term? It is very simple. Observe the previous term, it is p3. I am going to write down p4 into d to the power n minus 4 y divided by dx raised to n minus 4 and so on. Finally, you can write down p suffix n minus 1 into dy by dx plus pn into y is equal to x. So, this is the nth order linear differential equation. Then you may ask, this equation containing p1, p2, p3 so on are constants or are the variables? Is it clear? That is why here what I have written, where p1, p2 so on are and x are either constants or functions of x only. Is it clear? So, it means if you are replace these p1, p2 and so on by constants, then it becomes a linear differential equation with constant coefficients. Is it clear? What we have already discussed in the earlier sessions, right. So, now I want to treat p1, p2 so on as variables or functions of x, then it becomes a linear differential equation with variable coefficients, right. If the given differential equation is an linear differential equation with variable coefficients, then how do we find out such type of solutions? Now, we want to think or we want to find out solution of such type of differential equations. Is it clear? Right. So, now such type of equations you may call it as an homogeneous Cauchy-Euler equation. So, according to our curriculum, I want to discuss or I want to solve an equation of the type Cauchy-Euler equation, or sometimes we may call it as an homogeneous equidimensional equation. Both are same. Here Cauchy is name, Euler is also a name, right. Sometimes we may call Cauchy-Euler equation, sometimes homogeneous equidimensional equations. Is it clear? Right. So, here understand the process for solving a Cauchy-Euler equation is the objective. Is it clear? Okay. They have given a Cauchy-Euler equation. Now, I want to know that how do we solve a Cauchy linear equation. If the method is understood, then I will be very happy. Okay. Now, I am able to solve a Cauchy linear equation. That is my objective, right. And normally, a differential equation with variable coefficients are more difficult to solve. However, a Cauchy-Euler equation or equidimensional equation is an exception. It means a linear differential equation with variable coefficients are difficult to solve, but if the given equation is an Cauchy linear equation, very easily you can find out the solution of such a type of equations. Is it clear? Right. Say for example, they have given an equation like this. An equation like this means they have given a suffix n x raised to n d raised to n y upon dx raised to n plus a suffix n minus 1 into x to the power n minus 1 into d to the power n minus 1 y divided by dx raised to n minus 1 plus a suffix n minus 2 x raised to n minus 2 into d raised to n minus 2 y divided by dx raised to n minus 2 plus so on plus a 1 x into dy by dx plus a naught into y is equal to right hand side is a function of x is a Cauchy-Euler equation. It means now they will give this type of equation and we want to learn how do we solve this type of differential equation. As I have mentioned, this equation is also called equidimensional equation. Note that the degree of the coefficient is equal to the order of the derivative. Just to observe this equation. Is it clear? Right? As I have mentioned, the coefficient of d raised to n y upon dx raised to n is what? X to the power n. Right? You observe the power of x is n and here I have written d raised to n. Right? In the next term, you observe the power of x is n minus 1. What I have written? D to the power n minus 1. It means these two are same. Here I have written n minus 1, n minus 1. In the next term, what I will write? N minus 2, n minus 2. Right? So, what we are observing? N minus 2, n minus 2. Next term may contain x to the power n minus 3, d to the power n minus 3. Right? Its next term may be like this, x to the power n minus 4, n minus 4 and so on. Is it clear? That is why what I have written here, note that the degree of the coefficients is equal to the order of the derivative. So, this is an nth order differential equation. Is it clear? The degree of x is 1, the degree of dy by dx is also 1 and so on. Right? Okay. Now, they will give this type of equation. We want to find out the solution of this type of differential equation. So, it is called a Cauchy linear equation of the nth order. The above equation can be reduced to the linear differential equation with constant coefficients by the method of substitution. Okay. As I have mentioned, it is difficult to solve a linear differential equation with variable coefficients except Cauchy linear equation. Why this method is or this type of equations can be solved very easily? Because we are already familiar with a linear differential equation with constant coefficients, right. But here all the coefficients are variables and this equation is called Cauchy linear equation. Now, I am going to reduce this equation into a linear differential equation with constant coefficients. Once I am able to reduce to a linear differential equation with constant coefficients, then I know the method. I have already explained, you are already familiar with such a type of differential equations solutions, right. So, by using those methods, you are able to find out the solution. Here the question is how I am going to reduce this equation into a linear differential equation with constant coefficients. So, for that reason method of substitution plays an important role. It means this statement plays an important role, right. Now, I want to put x is equal to e to the power z. This implies z is equal to log x. This statement convert this equation into a linear differential equation with constant coefficients. Then you may ask, can you explain how it converts this equation into a linear differential equation with constant coefficients? It is very simple. Okay, I will put x is equal to e to the power z. This implies z is equal to log x. I am going to differentiate this equation with respect to x. So, what we can obtain? Dz by dx is equal to, we know that derivative of log x is 1 by x, right. So, therefore, dy by dx can be written as dy by dz into dz by dx. Is it clear? And dz by dx is what? Dz by dx by is equal to 1 by x. Now, I will substitute the value of dz by dx in this equation. So, what it becomes? Dy by dx is equal to dy by dz into 1 by x, right. So, what I have written here, dy by dx is equal to dy by dz into dz by dx. I have replaced the value of dz by dx by 1 by x, cross multiply. So, it becomes x into dy by dx, that is equal to dy by dz. Here d by dz can be written as capital D. Is it clear? So, capital D into y, that is why I have written here, where d is equal to d by dz. Okay. Now, I have obtained the value of x into dy by dx. So, can you tell me what is the value of x into dy by dx? It means in the given equation I can replace x into dy by dx by capital D into y. It means this term is converted into a linear differential equation with constant coefficient. Is it clear? Suppose if I replace x into dy by dx by capital D into y, that becomes the linear differential equation with constant coefficient. Exactly in the similar way, now I want to find out what is the value of d square y upon dx square. So, this can be written as d by dx of dy by dx. What is the value of dy by dx? So, dy by dx is 1 by x dy by dz. Here we have obtained dy by dx is equal to 1 upon x into dy by dz. Is it clear? Right? Okay. So, d by dx of 1 upon x into dy by dz. It means now I want to differentiate this function with respect to x. Okay. How I am going to differentiate? So, d square y upon dx square is as it is, that is equal to, I am going to differentiate 1 by x. So, derivative of 1 upon x is what? Derivative of 1 upon x is minus times of 1 by x square. Is it clear? So, derivative of 1 upon x is minus times of 1 by x square, right. So, dy by dz as it is, right, plus I will keep 1 by x as it is, right, into derivative of dy by dz. So, d by dz of dy by dz into dz by dx, right. Okay. Left hand side is as it is, minus times of 1 by x square into dy by dz plus 1 by x square into d square y upon dz square. Here I have obtained the value of dz by dx. dz by dx is 1 upon x. Here also dz by dx is there. I am going to replace this by 1 upon x. So, 1 upon x into 1 upon x is 1 upon x square. D by dz of dy by dz means d square y upon dz square, right. So, you observe 1 by x square, 1 by x square. I will take out 1 upon x square and I will cross multiply. So, you can obtain x square into d square y upon dx square, that is equal to minus times of dy by dz plus d square y upon dz square, that is equal to, it can be written as so d into d minus 1 by y. Is it clear? So, d by dz is common, or d by dz can be replaced by capital D, and it becomes d into d minus 1 into y. So, it means the value of x square into d square y upon dx square can be written as d into d minus 1 into y, right. And similarly, you can obtain the value of x cube d cube y upon dx cube. You can obtain exactly in the similar way, d into d minus 1 into d minus 2 into y, right. Suppose if you want to calculate the value of x raised to 4 into d raised to 4 y upon dx raised to 4, that is equal to, you can write down, so d into d minus, you can write down d minus 1, d minus 2 into d minus 3 into y and so on. Then you can substitute all these values in the general equation. What is the general equation? So, d into d minus 1, what we have written, x raised to n into d raised to n y upon dx raised to 1 can be obtained this value, or you can substitute all these values in the first equation, then you will get this equation, and this equation becomes the linear differential equation with constant coefficients. And we know the method linear differential equation with constant coefficients. So, we want to find out the general solution, right. So, in the next session, I am going to solve some examples about linear differential equations with variable coefficients. Thank you.